Let's begin by looking at a water wave. When a wave passes by, it has peaks and troughs. The amplitude is the distance from the calm water level to the peak of the wave. It's a measure of how much energy the wave carries. The higher the amplitude, the more energy it has. Now let's follow a single water molecule as the wave passes. Even though the wave energy moves towards the shore, the water molecule doesn't travel with it. Instead, it moves up and down, oscillating in place. So while the wave moves forward, the water itself just jiggles. To visualize this, we can draw a graph showing the displacement of the water molecule against time. This wave-like pattern lets us measure the amplitude and something called the time period. That's the time it takes for one full up and down movement or one complete oscillation. From the time period, we can calculate the frequency using this formula. Frequency is 1 divided by time period, where f is the frequency in hertz and t is the time period in seconds. Frequency tells us how many oscillations happen per second. So if a wave has a time period of 0.5 seconds, it has a frequency of 2 Hz, meaning 2 vibrations per second. Now let's change our perspective. If we look at the wave from the side and plot displacement against distance, we can see the wavelength. That's the distance from one peak to the next. It tells us how long the wave is. Wavelength has the symbol lambda and is measured in meters. We can now use the wave speed formula. Speed is frequency times wavelength, where speed is in meters per second, frequency is in hertz, and wavelength is in meters. Let's also check the units. Hertz is 1/second, and when multiplied by meters, we get meters per second. Perfect. Let's now view the wave from top down. What we see are wavefronts, lines representing all the points that are in phase, like the tops of waves. These help us understand the direction the wave is traveling. This, for example, shows how waves are bent as they pass through an opening. This is called diffraction. Waves like water waves, light waves, and electromagnetic waves are transverse. That means the vibrations are perpendicular to the direction the energy is moving. Imagine a rope being flicked. The rope moves up and down, but the wave travels forwards. But not all waves are transverse. Sound waves are longitudinal. This means the particles vibrate in the same direction as the wave is moving. We see areas of compression and areas of rarefaction. That's how sound travels through air. Although we often draw sound waves as transverse for clarity, remember, sound is a pressure wave, so in reality it's always longitudinal. Let's try a quick IGCSE exam style question. A wave travels with a speed of 340 meters per second and has a frequency of 170 Hz. Calculate its wavelength. Pause the video and give it a try. We use the formula speed is frequency times wavelength to rearrange it as wavelength is speed divided by frequency. Now we substitute. 340 divided by 170 is 2 meters. So the answer is the wavelength is 2 meters. Let's start with reflection, something we see every day in mirrors. When a light ray hits a surface like a mirror, some or all of it is reflected. But which rays get reflected? It depends on the surface. Smooth, shiny surfaces reflect more light. Rough surfaces scatter it in all directions. This is called diffuse reflection. Now, the important rule here is the law of reflection. The angle of incidence equals the angle of reflection. To draw it, first draw the normal, a dashed line perpendicular to the surface. Draw the incident ray coming at an angle to the normal. Then draw the reflected ray, leaving at the same angle on the other side of the normal. Always measure the angle from the normal, not the surface. Now let's look at refraction. This happens when light bends as it passes from one material into another. Why does it happen? It's because light changes speed in different materials. In denser materials like water or glass, light slows down. But here's the key point. Light always travels at the maximum possible speed. In a vacuum, that's roughly 300,000 meters per second. In other media, it's slower due to interactions with atoms. Let's make a drawing. A ray moves from air into water. It bends towards the normal because it slows down. If it goes from water into air, however, it bends away from the normal as it speeds up. The difference in angle is due to the change in speed. To calculate angles in refraction, we use Snell's law. n1 times sine of angle 1 equals to n2 times sine of angle 2. n1 and n2 are the refractive indices of the two media. Angle 1 is the angle of incidence, and angle 2 is the angle of refraction. Here's an example. Light enters glass with refractive index of 1.5 from air with a refractive index of 1 at an angle of incidence of 30 degrees. To calculate the angle of refraction, we rearrange the formula. Now we substitute the values. Don't forget to use the inverse sign to get the angle of refraction. So, as you can see, the light bends towards the normal as it enters a denser medium where its speed is decreased. Have you ever noticed how at sunset you can see the reflection of the sun of the water, but not at midday? That's due to total internal reflection. When light travels from a less dense material into a denser material, like air to water, it bends towards the normal. If the angle of incidence is large enough, light doesn't enter the water at all. It reflects instead. This happens when the angle of incidence reaches the critical angle. To find the critical angle, we can use the following formula. Sine of the critical angle is n2 over n1, where n2 is the refractive index of air and n1 is the refractive index of water. Substituting these values, we find that the critical angle for a water-air boundary is 48.8 degrees. So if the sun shines on the water surface at an angle of greater than 49 degrees, it will reflect off it. Question 1. A ray of light enters a glass block at an angle of incidence of 40 degrees. The refractive index of glass is 1.5. Draw a diagram showing the angle of incidence and the angle of refraction. Pause the video and give it a try. We start by drawing the boundary and the normal. Next, we draw the incoming ray and label the angle of incidence. Finally, we draw the ray entering the glass block, bending towards the normal as it slows down. Tip: always draw the normal line and show the wave bending in the correct way depending on the change in speed. Question 2. Light enters water with refractive index of 1.33 from air with refractive index of 1 at an angle of 45 degrees. What is the angle of refraction? Pause the video and give it a try. To answer this, we simply use Snell's law and substitute the values. Finally, we use inverse sign to get the angle of 32.1 degrees. When we think of light, we usually think of the stuff we can see, red, orange, yellow, all the way to violet. But visible light is only a tiny part of the electromagnetic spectrum. There are many other types of electromagnetic radiation, most of which our eyes can't detect, but we interact with them every single day. Let's start with infrared, which lies just beyond red light on the spectrum. Ever felt the warmth of the sun with your eyes closed? That's infrared radiation. It carries heat energy. The sun emits infrared waves, and so do heat lamps and remote controls. The main uses of infrared are night vision cameras, TV remote controls, thermal imaging, and heating systems. On the other side of the visible light is ultraviolet or UV light. It has more energy than visible light. The sun emits UV rays too, and while a little helps our skin make vitamin D, too much can damage skin cells. This is why sunscreen is so important. The main uses of UV light are sterilizing medical equipment. detecting forged banknotes, and killing bacteria in water. Now let's take a look at the lower energy side of the spectrum, microwaves and radio waves. Microwaves are used for cooking food in your microwave oven, sending signals to satellites, and mobile phone communication. Radio waves are even longer and lower in energy. They are perfect for radio, television broadcasts, Bluetooth and Wi-Fi. Radio waves are perfect for communication as they can travel far distances and are harmless to our bodies. Now we jump to the high energy end of the spectrum, X-rays and gamma rays. These waves carry so much energy that they can penetrate matter and damage cells, which makes them dangerous, but also incredibly useful. The uses of X-rays are medical imaging, also known as X-ray scans, security scans at airports. The uses of gamma rays are cancer treatment, also called radiotherapy, and sterilizing medical tools. When working with X-rays or gamma rays, doctors and nurses have to wear protective clothing made from lead or leave the room, as prolonged exposure can cause cancer. The sun emits all frequencies of the electromagnetic spectrum, and although X-rays and gamma rays are dangerous, Earth's atmosphere blocks most of them from reaching us. That's why astronauts in space need extra protection. There's no atmosphere shielding them. So unless you're heading to Mars next week, you're safe. State the type of electromagnetic radiation. A. Used in luggage security checks at airports. And B. Used by remote controls for TV sets. Pause the video and give it a try. The answer for A is X-rays. And the answer for B is infrared. And that's it for today. Don't forget to check out the other videos on our channel and like, subscribe and hit the bell icon so you never miss an IGCSE science tip from the learning curve. See you next time!